a contextual fashion. So let's just go get into this. Most of this lesson is all about example types. So here we go. I'm going to give you our first example. So we have, let me get my position here. So a 1,200 liter tank of water is filled to capacity at time t equals 0. The water begins to drain out of the tank at a rate modeled by R of t, which is measured in liters per hour, where R of t is given by the piecewise function, this right here. Find the average rate at which water is draining from the tank between 0 and 8 hours. So when you see a question like that, you're looking at average. That's the key word right there, average rate. Okay? And so they were looking for the average value. Okay? And since you are given they want the average rate at which water is draining, and this is the rate at which water is draining, so that connection right there tells you that you're using the formula. And so we just simply use our formula right here to answer this question. So our average is going to be 1 over b minus a, which in this case is 8 minus 0. So 1/8 from 0 to 8. And it is going to be r of t dt. Okay. Now we have a piecewise function. So we have to do each piece according to the separating point, which is at 5. So we're going to have to split this into 2, where it separates at 5, and so we're going to have the 1 over 8, and then we're going to split this integration. So the first one's going to start from 0 to 5, and so we're going to use this one right here from 0 to 5, 600t over t plus 3 dt, and then to that we're going to add the other one from 5 to 8, and we're going to use the 1000 e to the negative 0.2t dt. So that's our setup right there, and at this point we use a calculator to help us address this issue. So again, I'm going to show you real quickly how to do this on the calculator so that you can kind of mimic it and follow it later on. Let me get my calculator up here and get it started. So we're going to do number 1, and we go to menu, and we're doing calculus, and we're doing integration. Okay. Now before I push this button over here, I just wanted to show you where it was at. Before I do the integral, I want to keep in mind that I have a 1/8 out in front. Okay. So, but since I'm already in this spot right here, I'm going to put the plus, put number 3 in here, the integral. So I have that right there. Okay. So then I can just type in everything that I have, and what I'm going to do is I'm going to back up, and I can use the arrow keys and I get out in front, and I can put a fraction button, and I can do 1 over 8, and then I'm going to go off of that, and I'm going to put all this in parentheses, so I can do like that, and now everything's going to be in the parentheses when I get done here. So this is going to go from 0 to 5. You just tab through everything, type that in, 600, don't use a t, use an x, and down here I have x plus 3 dx, and then I'm going to add to that another integral, and that one's going from 5 to 8, and that is 1000 e to the negative 0.2 x dx. So that should be everything looking right there of what we typed in over here. It should be the same. Okay, and when it is, you just hit Control Enter, and it gives you a number, which is what we're looking for. Round your answers to 3 decimal places. Okay, so this right here would be an approximately equal to 258.053. So when I give you these decimal answers and stuff like that, just note that that's what I did on the calculator. So if you have any issues with that or need assistance with that, please let me know, and we can talk about that in the class time. All right, so there's my number. Find the average rate of the water draining from the tank between 0 and 8. When you write an answer out like this, a number is not enough. Usually units are involved, and they want you to explain what's going on. So what is this answer in context of this problem? Which is really how they're going to ask you a lot of questions. This is the average rate at which water is draining from the tank between t equals 0 and t equals 8 units, hours. So the average rate at which water is draining from the tank between 0 and 8 hours is 258.053 liters per hour. And so you want to make sure you have the proper units on things. Identify your time span. Use the question they asked you to answer the question they want. Okay? Let's look at another example here. Okay. Here I give you a table of values. T is in hours. From the table I can see I got vehicles per hour. That's my rate. On a certain weekday, the rate at which vehicles cross a bridge is modeled by the differentiable function R between 0 and 12, where R of T is measured in vehicles per hour and T is measured in hours since 7 a.m., where T equals 0. The value of R of T for selected values of T are given in this table. Use a right Riemann sum to approximate this right here, and then use proper units. Interpret the meaning of this answer in context of the problem. So this is usually how it's displayed for you and what they want you to do for this. Okay? So let me go ahead and give myself some room to write. So we want to do a right Riemann sum to approximate that. So that's how we start. So 1 over 12 from 0 to 12 R of T dt will be approximately, and now we're going to do a Riemann sum, a right one. So it did not give us how many to do, so we'll just do the simplest one. We'll just use with a given table to assist us. So we're going to do a right Riemann sum. I do recommend highly when you do something like this to draw a quick sketch. It doesn't have to be pretty, but it should help you out. You can even do it up here if you wanted to. And what I'm trying to establish is I want to establish my intervals. In this case, they're all equally spaced, so this is a lot easier. But you should get in the habit of doing this every time so that you can, when they're not even, you can still do the problem fairly easily. And so we're going to do a right Riemann sum, so we're going to start at 2. Okay? So this is the right for this interval right here. This is the right. So 2 is going to go up to here. 4 is going to go up to here. And this is this number, 3653. This is 3442. Again, it doesn't have to be perfect. It doesn't have to be accurate. It just has to represent. And then this one over here is that, 3604 at 10, 1986, and then at 12, 2201. So this gives me the numbers that I'm going to be using as a right Riemann sum. Okay? So then don't forget the 1/12 here. So my answer is going to be 1/12. So the Riemann sum is for the approximation for this integration. The 1/12 is still out in front, so we still need it. So each of these bases are equally spaced, so they're all 2. So I'm going to do 2 times each of those numbers. So it's going to be 2 times their 3653. And you want to make sure that you write this out. And then this one is 3442, and so forth and so on. And then 2 times 3604, 2 times 1986, and 2 times 2201. So that is my right Riemann sum for this approximation. We can use a calculator to assist us in this. Remember, this is an approximation, but this is what I'm actually getting right here. Okay, so when I do this right here and I get an actual answer, I get this fraction. And then I can change this to a decimal. You can leave it like that. That's an actual answer. Okay, that's the actual one. If you want to approximate it again, then you can take this as a decimal and you get this answer right here. Now, that's part A. Part B is to interpret this answer in proper units in context of the story. So again, use the story question to help you answer your question. Use all the context of the story in your answer so that it makes sense. So we found the average rate. Okay, this is the rate of what? Measured in vehicles per hour that cross the bridge, correct? So this is the average rate at which vehicles cross a bridge on a certain weekday between what? What's my time frame? What's my interval? It's a 12-hour interval starting at 7 a.m. So in context, so weekly between 7 a.m. and then 12 hours later, which would be 7 p.m. And it is approximately 2982.667 vehicles per hour. So that is your answer in context. Okay, let's look at some more information. So to do that, I need to come back to our notes and talk about the particle revisited. So let me get this in position so you can read it. Okay, so particle. So things to remember: the position function, S of t. They can use other names for this, x of t, y of t, just depends on what they want. But the position function, the velocity is the derivative of the position function. The acceleration is the derivative of the velocity, which is the second derivative, and the acceleration is the second derivative of the position. So in doing this problem right here, we need to remember these formulas right here. These are the questions they're going to ask you in some way. So we want to make sure you understand the difference between them and what's going on. So displacement. The displacement is basically the net change in distance that's traveled. Usually I do on this one right here, so just imagine you're going from school to home and you decide to do a roundabout way. Okay. The displacement, though, is where you started from and where you ended at the journey, and that direct distance, that is displacement. The actual journey that you traveled, all the different ways you went, that is in the total distance traveled. Okay, the displacement is the change in position. Your change in position is displacement. The total distance that you traveled is the whole entire route that you went. Okay. So you want to make sure that you make that distinction. And you'll notice over here, because in a total distance travel, I can go forwards and then backwards, I can backtrack or whatever. So that's why it's in an absolute value symbol, to make sure we take all those distances and directions as positive values. The last thing they're going to ask you to do is they're going to ask you to find a position of a particle at a certain point, okay, at a certain time. And so to do that, you need to know this formula, which is very similar. You're going to see this in many different formats. This is similar to that fundamental theorem of calculus that we talked about. Okay, here's S at some point. This is the initial position that you started from, and notice this is the displacement. So from this point I'm starting at, travel through that distance, okay, in a straight line kind of a thing. So it's your initial position plus the displacement will get you your final position. Okay, so you need to know those questions right there, and then that's going to help us answer our next question. So let me move this out of my way. Bring this back down so you can see it. So here we go. A particle moves along a straight line with acceleration modeled by a of t equals 4t. The velocity and position of the particle are modeled by v of t and s of t respectively. Given that this is equal to -2, so v of 0 is -2, and s of 3 is 0, determine the position at 6. Okay, so here's how we begin. Here we go. I gave you the acceleration. Okay, so you need to get to the position, which means I need to integrate. If the derivative if then antiderivative of the acceleration would be the velocity. So this means that the velocity function is the antiderivative of the acceleration function, which means I'm going to integrate 4t dt. And I'm going to use our techniques for integration of this quantity right here. Going to take this, and the 4 is a constant, and so it's raised to the power 1 divided by the raised exponent. So when I do that, this is going to equal 2t squared, and then because there's no limits, don't forget, plus a constant. So that is v of t. But I can't just have a constant, unknown constant here, so I have to use what's called the initial conditions, which is those right there. V of 0 is negative 2, so then I'm going to plug those in, and so v at 0 is 2 times 0 squared plus a constant, and that has to equal negative 2. So then I can use this equation right here and find what c equals to, which is negative 2. And then I can replace that into here and then get my full-blown velocity function, which is 2t squared minus 2. That is the velocity function. Well, what is the velocity function in relation to position? Well, the position function is the antiderivative of the velocity, which means that s of t is equal to the integration of the velocity function. So I need to integrate this newfound velocity function, dt. And again, using our technique for integration that we have already established, we have 2/3 t to the third minus 2t, and again, plus a constant. So I got to find that c, and I know that initial condition right there for s. So using the same technique I did over here, s of 3 is 2/3, 3 cubed minus 2 times 3 plus a constant, and that should equal to 0. So then if I solve this out, I should get c is equal to negative 12. And so now I know my position function, s of t, is 2/3 t to the third minus 2t minus 12. Now I can answer that question. I now have the function for s of t, and so I just simply need to plug in 6. 2/3, 6 to the third, 2 times 6 minus 12, and you can work this out and you should get 120. And that was your answer. Okay? So this process you're going to use quite often. It's a simplified version of stuff we're going to look in more detail in the next unit. This right here is the very basic beginning forms of what's called differential equations, but we'll talk more about that in the next unit. Okay? So I want to look at another example together. So here's another problem here. A particle moves along the x-axis. The velocity of the particle at time t is given by v of t, and the acceleration of the particle at time t is given by a of t. Which of the following gives the average velocity of the particle from t equals 0 to t equals 8? Okay, so this is a kind of a question you might see on the AP exam. They're going to throw all this stuff at you here, and we have different kinds of velocity or averages, excuse me, and so look at these answer choices and see if there's any that we might be able to eliminate. Well, I hope you understand clearly that this one is not going to be involved at all, because we don't have a rule that has the absolute value here. We're not going to use this one. Okay? But this is the difference quotient, and this is the difference quotient, you know, and we've done these before for averages. I mean, average, the secant slope and all that kind of stuff is the average rate of change that we learned way back in the day. But then so is this. So how do I know which one it is? How do I know what I'm looking for? How do I know I don't get confused? Okay? Well, very simply, it's this. If they're talking about the average velocity, then this integration symbol works with the actual function that you want to find the average of. Since this is a velocity function, and I'm looking for the average velocity, then this notation will produce the average velocity because I was given v of t and such. These are not the answer because the secant slope works on the function above what I wanted. So the average velocity in a difference quotient would require us to have the position function, not these. Okay? This is the average, 8 minus 0. This would be the average velocity based off the position function. This is the average velocity based off of the velocity function. They produce the same answer, okay? But you need to know when to use which one. And so that's what I have written down here. Okay? So that's a very important way to help you distinguish between which one to use and what. Okay? So let's look at another example to help us answer some of these things, and then I'm going to show you some extra notes that are involved in this one. So a particle moves along the x-axis. The velocity of the particle at time t is given by this expression right here. What is the total distance traveled by the particle from 0 to 4? So total distance, that's pretty straightforward. Write your formula down. Your total distance is the integration from 0 to 4, because they said from 0 to 4, and is the absolute value of the velocity function. That is your total distance traveled. Do I have the velocity function? Yes. Velocity is given by this right here. They just expressed it in words instead of symbol notation. So I can replace that with that, and now I have this. And this is 8t minus t squared dt. Now at this point you can go ahead and type this in the calculator and get a response, okay? But sometimes this might appear on the non-calculator portion, so you should be able to handle this. And so a lot of times when you look at this stuff, you're going from 0 to 4. Think about what that function looks like graphically, because I'm looking at an absolute value. And if that whole entire graph, and if you looked at it, this entire graph, and you graphed it, you'll see that this entire graph from between 0 and 4 is always going to be above the x-axis. Okay? And so then the absolute values are pretty much redundant. Since everything is going to be above the x-axis anyway, it's already positive. You're just saying take something positive and make it positive, so you don't need that. Okay? So with that, if that happens, and you know that this entire function is going to be positive for these interval from 0 to 4, you can just drop the absolute values, which makes this easier to integrate. And you can just drop that and you can integrate this function and get the same exact answer. If it was on a calculator, I would just type it in. So using our integration techniques, this is going to be 4t squared minus 1/3 t cubed, evaluated from 0 to 4, and you plug in the upper, and 4 squared minus the lower. And if I plug in 0, everything here is going to be 0. And so you work this out and you get the exact answer, 128/3. I always want to do an exact answer if possible. Okay? And so with that, let me go ahead and show you this right here because I have a little side note so you can stop and write down what I said earlier. So because v of t is greater than 0 for all the t's in this interval, we don't need the absolute value symbols, so remove them and make the integration easier. Okay? Or again, you can just use your calculator. So let's look at the next example I have down here. A particle moves along the x-axis from 0 to 4. The velocity is given by this equation right here. The position is s of t. It is known that s of 0 is -1. Find the position of the particle when t equals 3. So again, this is a position question. So we have that formula that we talked about. So the s of b is s at a plus the displacement from a to b of the velocity. So position, starting position, velocity. So let's plug in our numbers. S of 3 is s at 0 from 0 to 3 of the velocity function. And then I can just plug in all my numbers that I know. So this is equal to -1. plus, and then I can integrate this with my calculator, replacing this quantity right here for V of t, and then I will get on the calculator 4.970. So I just wanted to show you how to do that. This right here, you would need to replace with that to use your calculator to answer this question. And if you need assistance with this at any time, please let me know. Let's look at another example that we have. A lot of examples. Make sure I get the right one here. Yep. So let's look at this problem. Okay, same thing again. Particle is moving along the x-axis. Particle's position is x of t this time. It's not explicitly given, so I don't know what it is. The velocity of the particle is given by that expression right there. The acceleration of the particle is given by that right there. And when x is 0, the value of the position of the function at 0 is 2. That's your starting position. Find the average velocity of the particle from 0 to 6. So we're just going to go through the different processes here. So for part A, average velocity is 1 over b minus a. From 0 to 6 of the velocity function. And then you would type that part into the calculator, and you'll get an approximate value. So take the time here, use your calculator, practice that out. You need to practice using the calculator. So practice typing it out, and you get 1.949. Okay. Part B, what is the total distance traveled by the particle? So the total distance, notice how I'm displaying it here, is the integration from 0 to 6 of the absolute value of the velocity. So you want to make sure you always write that down so everybody knows what you're doing. Plus, on the AP exam in the free response portion, this is sufficient. You do not need to type that in or write that down as long as it is present in your question. Okay? You can write it down. Just be careful, be extra careful that you do not have a transcription error. This will be e to the t over 4 plus 1 dt, and then use your calculator here. Again, take a moment, pause, and type this in and make sure you know how to do it. All right, if you did, you should have gotten this answer right here, 573. The last one here is the particle changes direction exactly once. Find the position of the particle at that time. Okay, so this requires us to do some thinking here, making sure we understand the question that's being asked. The particle changes direction exactly once. Okay, the particle is implying the position changes direction. Okay, direction changes occur when the velocity changes sign, and those happen when the velocity is equal to 0. So these are the things that should be going through your head. So if I need to find out when the particle changes direction, then I need to know when is the velocity equal to 0, because that's where it's going to change direction, provided the part that it does change direction on either side of that. You can draw a quick sketch of this graph over here to confirm that you know what's going on, but you need to establish when this occurs. Okay, and so then you can use the calculator again to find out when this is equal to 0. You can look at the graph of that to help you illustrate what's going on, and so then you would find out that it will change direction when t is equal to 5.19552. And however long this number is, you cannot round it off. You have to use the entire long number. Now there's a way to do this where you can just take this and store it into a value on the calculator. Okay, there is a store feature right here. You can store things as a variable that you can then use in your problem. Okay, and so we will discuss that in more detail in class, all right, so that you can see how that is done. The video is getting a little long, so I'm going to keep going. So what you do is you store this in, and you can do this on the test too. You can say this right here, I'm going to call capital B. Okay? And then once you've done that, once you've established that this long number here is going to be capital B in all of your work, you can now use that in your answer. Okay? So we want to find out the position at that time. Well, that's the time is B. So the position at B is equal to the starting position. Okay? The starting position is 2. So this would be 2 plus the integration from 0 to B of the velocity function. That's the displacement. Starting position, displacement. And then you can type all this into the calculator. And if you stored it in B, you would just type B up here. Don't type the number, you type B. And guess what? You will get this answer. Give it a try. Pause it. Try it yourself. See if you get the right answer. So here's what you should get. 14.135. And so that's how you can do a couple of things there. All right? So before we do the next example here, we need to talk about some other stuff. And you can see this picture right here. Here's the problem I had before. I used lowercase b the first time, but here's where the particle changes position. We find that point, which is that one right there. And there's the problem. So here are some other things we need to remember about the fundamental theorem of calculus as we go on to the next extension of our problems. So take a moment here, try and look at that. So the fundamental theorem of calculus, remember, if f is an antiderivative of a function f for all values of x, then this is true. This is how we evaluate our functions after we integrate them. We find the antiderivative and you plug in the upper limit minus the lower limit. If I do that, I'm thinking about this thing here as the area under a curve between A and B. If I think of it as an accumulation of net change, then it looks like something like this, where this would be the derivative. It's still the same thing. This is the derivative of that, and this is the derivative of that. It's the same thing, but it's a different look. Okay? And it kind of like helps you remember things in a sense that so that it keeps it separated. But let's look on to what's going on here. Over here, we're adding all the rates of change to get a change in between. So let's look at this down here. See if I can get this to focus a little bit more. Okay, so we're going to use the accumulation model with a definite integral. If f of a is known, the starting position, and the rate of change between a and b is given by a derivative, then I know this to be true. This is basically like the position, but it's doing it for other rates, not position functions, but it's the same thing. Okay, and the position, final position that we had for particle, this was the end position, this was the start position, and this was the displacement. And it's kind of the same thing. But for non-particle problems, these just take on a different name. This is the end point, if you're looking at, this is the starting point, and this is the net change. What changed overall? You know, that part that's changing. And so this right here is just saying that if I needed to do an integral switch here with the limits, I can. Everything will work out well as long as, and these numbers here have to be matching. Okay, so that has to match that, and that has to match that. You want to make sure that's occurring, and if that's true, then limit changes can actually occur also. So we're going to look at now some new problems through the lens of this instead of the particle, but it's very similar to the particle. It's almost identical to the particle problem's position problem. Okay, and all that stuff that we had before. So let's look at another example and find out where it is. Here we go. A function is known to be increasing at a rate modeled by that expression right there, that function. So f prime of x equals this. It is known that at x equals 4, the function has a value of 15. Find the value of the function at 7 and at 2. So you're going to be asked to find a lot of values of functions. So we're going to use what we just established. So f of b is f of a plus its net change, f prime of x dx. And we're going to do that with this problem. So what is f of 7? F of 7 is F at 4, the start position, because we're starting at 4, okay, plus the displacement. So this is going to go from 4 to 7 of f prime of x dx. And then we just add in our numbers and stuff that we know. This right here, they told us is 15. We're going to integrate from 4 to 7. This expression, this f prime. And then I can use my calculator for this. You can do it by hand if you wanted to, but it's a sine function, so it's going to give you weird answers anyway. And so then I can use the calculator, and I can approximate f of 7 from the calculator work. Round your answers always to 3 decimal places, and so then that's f of 7. Okay, f of 2, same process. F of 4 plus the integration from 4 to 2 of f prime of x dx. See, these have to match, those have to match. When they do, this is all true. Then I can do what? Well, I can take this and flip it if I wanted to. I can actually integrate it, because I'm going to use a calculator this way. The calculator will do it for us. I don't have to. But if you were on a non-calculated portion of the test, you might want to do this. So f of 4 was 15, because these limits are backwards. So this will be 15 minus the integration from 2 to 4 of this. And I'll just go ahead and type it in. 3x plus the sine of x dx. And then I can work this out and integrate it by hand and evaluate this. Or I can just simply, again, use the calculator to assist me and get negative 3.237. A lot of times for very difficult or semi-difficult problems, that will be on the calculator portion of the test. So that's how I can find position values. And you're going to do this quite often. So let's make sure we can do that, okay? Here's another example. Got a lot of examples in this lessons. Different looks of different things, okay? Water tank is leaking at a rate modeled by that. V is measured in gallons, T is measured in days since the leak started. No water has been added to the tank, and the tank held 24,000 gallons when T equals 2. How much water is in the tank 4 days after the leak started? Okay? So again, we're going to use that formula. They're literally asking us, this is the rate at which water is leaking out. So V is actually the thing we're looking for. And I want to know, what is V at 4? The volume at 4. Okay? Well, I have a starting value. When T was 2, I had 24,000 gallons, so that means V of 2 is my start value. And then I need my displacement from 2 to 4, because that have to match. And I'm going to integrate the rate at which water is leaking. And so then I can plug in my values for these things. And then I'm going to integrate here from 2 to 4 of this function, which they gave me as negative 25 pi over the square root of t dt. Again, you can try and do this by hand if it's possible for you to do, which it is. It just takes a little bit more effort. But I can use my calculator and pause it and type this into your calculator to make sure you get the right answer. And here we go. So you're going to get 23,907.985, and don't forget your units. Gallons. Why is it in gallons? Because I'm looking for a volume. How much water is in the tank? How much water is in the tank? That is measured in gallons. Okay? Let's look at this one. A printer is going to publish multiple copies of a document. While printing this document, ink is being used at a rate of that, measured in ounces per minute. If the printer started with a job with 5 ounces of ink in the cartridge, how much ounces of ink will remain in the cartridge in 3 minutes? Okay? So you can designate your answer, your antiderivative however you want. I did it as, since we're looking for ink, I used capital I. So what is the amount of ink left at 3 minutes? So for this, I need to know how much was at the start, which I know. Now, this one's a little twist on things, and I'll explain it to you in just a moment, how you can tell when to do this or not. This is going to be a minus. from 0 to 3 r of t dt. Now this is important to be aware. Read the questions carefully. Okay? Take a moment. Think about it. What are they actually giving you? This is the amount of ink that is being used. This is the rate at which it's being used. But the question I'm asking you is how much is left in the cartridge? The amount left in the cartridge is the amount I started with minus the amount I used. They gave this to us in a kind of like in a positive fashion. Whereas in this one up here, you can even see that they gave it to you as a negative value. So this knows that we are decreasing. Okay? It is leaking at this rate. But here, okay, so when I integrate this thing, I'm getting the total amount that has left, is what I'm getting at here. Okay? Here, I'm given a total of how much I used. It's not how much I was left, okay? It's not how much, it's how much I used. So I needed a total amount minus that, and that's why there's a minus sign here. And then you can just, again, work this all out, and you can get it as 5 minus this. If you need to, you can also do it in another fashion, which I'll show you. I won't write it all out. And you'll get 4.372 ounces. And so that's how you can do that one, and that's why it's an R is minus. So I will give you this, if I have some side notes, I'll let you write it down so you can see it. And an alternate way to look at this problem also. So this is saying over here what I just told you. This amount is a minus because ink is being used, and R is a positive value of how much is used. I of t is how much of ink is left in the cartridge. Okay. In the previous example, V prime of t was given as a negative value at the start. So be careful as you read these things. Okay. You can also have done it this way, found the total amount of ink that was used, and subtracted it from what you had starting at. So the amount left after 3 minutes is what I started with minus what I used. Again, an alternate methodology for this process. All right. So let's take a look at another example. And before I do that one, I want to talk about this. Just a little side thing here, what we're talking about here, to be careful on stuff. Context problems can be a little confusing, so read them carefully. Focus on what do I know, what does it represent, what am I trying to find, and does my answer make sense? So when you do this, keep that in mind. Take a moment to look at things carefully, okay? And try to discern what the players are and what the signs they are and what they're asking you. Very, very important. So we're going to look at another one. We've got an oil tanker. All right. So oil tanker given to you as a table of values. We can see that clearly right here. The hours is T. R of T is going to be thousands of barrels per hour. Let's read. The oil tanker is in port and is being filled with oil. The table of values is shown with observed rates of oil being pumped into the tanker over a 10-hour period. 2 hours into the process, there are 110,000 barrels of oil in the tanker. Use a right Riemann sum to estimate the amount of oil in the tanker at the start of the 9th hour. Okay? So, we want to estimate the amount of oil in the tank at the start of the 9th hour. That means a total amount of oil in the tank. So we need to keep at it and go at it from that perspective. So the total oil at T equals 9. Okay? So then that is the starting amount, 110, plus the integration from 2 to 9 of my rate. So this I have, this I need a Riemann sum for. So let's do a right Riemann sum for this integration only. So I'm only going to use the 2 to 9. Okay? So I'm starting at 2. So the first interval isn't at 2, it's really from here. So if I look at if I drew a little quick picture here, I'm starting at 2 and 4 and 7 and 9. that is my first interval, so I need the right value, which is at 4, and then I need the value at 7, and then I need a value at 9. So do this little picture to help you see what you're doing. So for my right Riemann sum, this from 2 to 9 of r of t dt is approximately 2 times 75 plus 3 times 75 plus 2 times 70. And so that is 150, 225, 140, and then these numbers right here I'm going to add to this over here. So this is going to be approximately 110 plus 150 plus 225 plus 140, and that gives me a value of 625. So real quickly, there's what? 625,000 barrels of oil in the tanker at time t equals 9 hours. So that would be your answer for that right there. Okay? So we have one more example to go. Here we go. Last one. The balloon. And I forgot the picture. So let me draw the picture real quick. Okay. Very quick sketch of the picture. So we have this right here. And let's put a mark up here. This is going to be 50. And here it's going to be here. And it goes to here. And here. And it does that. Totally forgot the picture. So this is going to be 60, 120, and this is 540, just so you know. Okay? This is my velocity, or my v of t. In this case, I have no idea why I put a v there. But anyway, I think I used it in the problem. A balloon is being used to move sensors to a different altitude and is anchored to a ground by a cable on a winch. The cable made of 3 line segments. The graph made of 3 line segments represents v of t. The rate at which cable is being let out or pulled in. It is measured in meters per second over the time interval measured in seconds. T equals 0. The balloon has an altitude of 10 meters. Assuming the balloon moves straight up and down, find the balloon's altitude when t equals 540 seconds, or 9 minutes. Okay? So using our basic thing, I need a function, the antiderivative of that. So I'm going to use altitude, A. So what is the altitude at 540 seconds? Well, it is the altitude at the start plus 0 to 540 of v of t dt. I don't have v of t dt. How in the world am I supposed to do it? Well, that's what the picture is all about. So this, I can consider this to be what? The area under the curve. So I just need to find the area of that over here. So from 0 to 540 of v of t dt is 1/2. Add the bases times the height, 22,500. And so then this over here is going to be 10 plus 22,500, which is 22,510 meters. So this one is designed to show you that I can find these things by a Riemann sum, or I can find it by geometric areas, or I can do it by integration. All different types of ways to do this problem, so be prepared for any one of them. And so that concludes this video. Sorry about the length, but it's a lot of examples.